Second harmonic generation, or SHG microscopy, is a powerful technique for label-free imaging of collagen present in the cornea and sclera of the eye. Its high sensitivity enables imaging of the structural changes of collagen fibers related to eye tissue malformations and diseases such as keratoconus and myopia. The VOBio, the Visual Optics and Biophotonics Laboratory at the CSIC in Madrid, led by renowned Professor Susana Marcos, is a world-leading research group for the study of non-invasive in vivo imaging techniques, including SHG microscopy of the eye. We've established a collaboration with Dr. James Germann, an expert scientist in SHG microscopy, and we visited him at the CSIC in Madrid.
My research centers on measuring ocular tissue, specifically the cornea and the sclera. And what we'd like to see is how the collagen fibers, which make up the cornea and the sclera, are interweaved and are laid out in both of these tissues. One of the things we're always looking at is identifying biomarkers in ocular tissue to let us know if there's a disease which is starting to develop. So one of the diseases, keratoconus, you can start to see that the interweaving of the anterior of the cornea decreases. So the amount of depth of interweaved tissue actually goes down. So it's one of the potential warning signs that you could use. And you can see where the collagen interweaving decreases using second harmonic generation. Another thing you can look at is how straight or organized the tissue is. So we've developed a quantitative standard that we've called the order coefficient. So using the order coefficient, we can see that in normal tissue, it has a set amount of order in it. So the fibers are straight, they're going in one direction, they're not wavy. But in keratoconic tissue, we've seen that they are less straight, they have sort of less organization. One other thing we want to look at in the future is we'd like to see how myopia develops in the posterior sclera. So myopia is an elongation of the globe. And one of the things which happens is that the structure of the collagen fibers in myopia, they actually redistribute. The structure changes. So you actually break down your collagen and it reforms to help adapt to the elongation of your ocular globe. So one of the interesting things we like to see is, one, what that looks like on a microscopic scale, and two, how we can identify it and stop it in its tracks.
Dr. James Germann has a long international track record in non-linear imaging of organic specimens, including collagen. He explains the unique attributes of SHG microscopy and the key elements to consider when building an SHG microscope.
As it turns out, the collagen fibers, which your tissue is composed of, they are an excellent upconverter of photons. So what that means is, what happens is you have two photons and they interact with the collagen molecule. And both of these photons actually convert into one photon without any loss of energy. So what you get is you get exactly double the frequency, or half the wavelength of photon. And you can collect all these photons. So second harmonic generation it's a self-sectioning microscopy technique, which means that you don't have to worry about spatially filtering where you're looking to in the sample. You're only looking at the focus of the microscope objective. So you're able to look layer by layer by layer without having to introduce anything other than a detector into your detection arm. Here at the Visual Optics and Biophotonics group in CSIC, we have made our own second harmonic generation microscope. And kind of with all microscopes, the first thing you need to consider is what your application needs to be. So for us, because we want to look at second harmonic generation of collagen, the most important thing to start off with is your laser source. And you need to have a laser source which is able to interact with the collagen in order to produce second harmonic generation. So something in the infrared range converting towards the blue, somewhere between the blue and ultraviolet range. The second major component you need to think about is your microscope objective in order to have a very tight focus. And for that, you'll also need to have your photons, as many photons in one place at one time as possible. So you need a microscope objective to focus really small. And you also need to have a source which is pulsed. So you need a pulsed lasing source in order to make sure that all the photons arrive more or less at the same time. So the second harmonic generation process it's a very, very short window, so to speak. So if the photons don't arrive within a femtosecond of each other, they can't interact with the collagen at a sufficiently rapid time, and they just kind of scatter off and do their own thing. And finally, you need to think about your detector, what wavelengths you want to record the emission photons at. So fortunately with second harmonic generation, you can easily calculate what wavelength ranges you need to record at.
As part of our collaboration, Dr. James Germann has integrated Phyla SCH femtosecond fiber laser into his SHG microscope in order to image the cornea and sclera of the eye. He explains his experience using this laser, which delivers a broad bandwidth across 900 to 1200 nanometers and extremely short femtosecond pulses of the order of 15 femtoseconds at the sample plane.
I've found that using the SCH, I have been able to replicate the images I've been able to take with the MiTi laser. So the wavelength ranges of the SCH they're sufficient that we can collect the images of the fibers and using our already built second harmonic generation microscope. And I like the ease of operation that the SCH uses. So as a comparison, the current laser that I'm using, takes a while to warm up. There are some parts that need replacing. And usually I have to wait an hour or two before I can even begin aligning the system. But the SCH, it's very turnkey. Flip a switch, and then you turn it on. It's very compact as well. So if you're starved on, or if you don't have a lot of table space, which sometimes I wish I had more table space, it's very easy to put the laser in there and work with it that way. With porcine eyes, porcine samples, which can range normally from 800 microns before you excise the tissue. And after excising, the tissue tends to swell a little bit, so it can go even up to a millimeter. In that transparent tissue, I'm able to use the SCH to go all the way through the millimeter of tissue. And then I've also done experiments with sclera. So with sclera by itself, virgin sclera, I'm able to image down to about 150 microns before I start to lose signal due to scattering of the tissue. Actually, one other advantage of the SCH compared to the laser we're using now is that the pulse is it's about a quarter of the length of the laser we're using now. I haven't seen any additional autofluorescence, not that I've observed. So we're still able to get clean images of collagen out. So I wouldn't say that autofluorescence is any more of an issue than it would be in a other laser. But this also has the added benefit that, say if you did want to do a fluorescence application, that you could excite multiple fluorophores at the same time.
Phyla SCH, revolutionary technology by Phyla.